My name is Wan Yu, and I'm the Chaire Professor Junior hosted in IEMN, which is a microelectronics lab, mainly making thin film by clean room processing. And so today I was asked to talk about my research more in a broader sense. So my research in IEMN focused on using advanced characterization, especially atomic force microscopy, to try to understand certain aspects for energy storage, especially battery research. So before I kind of show you very quickly what I do for my research, I want to zoom out a bit, give an overview. Why do we care about energy storage? Why do we talk about batteries, electric vehicles so much? So why do we need energy storage systems? You can see on the left figure here, that's the global energy consumption by source. You can see for the past 200 years, ever since the Industrial Revolution, we have an exponential increase in global energy consumption. If you look at what source they have been taking from, 80%, more than 80% of the energy is coming from fossil fuel. So how about France? If you look at the right figure, France, this is only for more recent data. The total consumption, energy consumption now is about 1.4% of the global consumption by France only. Although France has been very good in the sense that majority of the electricity production are coming from nuclear, which is clean energy. But if you look at total energy consumption, France is also relying on fossil fuel about 50%. So you know where this is going. With all the use of fossil fuel, we are burning them off, breaking all those CC bond, CH bond with air. So of course, this produces a lot of CO2 or other greenhouse gases. So we have a direct correlation. How much we're using the fossil fuel will generate certain amount of CO2 or greenhouse equivalent. So you can see today, every year we are pumping out more than 40 billion tons of greenhouse gases. Of course, if you look at the global temperature, there's a correlation. You can see the line I put 1950. There's a direct correlation with the global warming. So this leads to whatever you are seeing recently with the extreme weather condition. There is huge fire in the south of France just last month. So those are going to cause a lot of extreme condition, leading to endangering lives, properties, business, also endangering certain species. So some of the species will go extinct, unfortunately, with this trend. This is the reason why 10 years ago, a lot of countries gathered in Paris for the Paris Agreement, COP21. Every country agrees, try to pitch in whatever they can to replace the fossil fuel source by renewable energy sources. Right now, there are majority 5 different types of renewable energy sources, the solar, wind, hydropower, geothermal, and biomass. So in this agreement, every country, depending on what they can do, they will put out their roadmap towards net zero carbon emission by 2050 gradually. So their goal is to reduce these 3 colors correspond to the fossil fuel. You can see we are trying to go gradually to decrease the amount of fossil fuel dependency on the fossil fuel. However, in this picture, there is a challenge that is not mentioned. Some important part of the energy, the renewable energy are sporadic, especially for the solar and wind, meaning you cannot ask the wind to blow whenever you want to watch TV. So there's a problem. That's why we need energy storage systems to pair up with all the renewable energy sources so that when the wind blows, you store the energy immediately and you draw them out, use them whenever you need them. So that is the main importance of energy storage systems. That's why there's so much talk about it. If we want to shift towards to this net zero carbon footprint, energy storage system is also together in this picture. Okay, So there are quite some different energy storage systems. There are thermal, mechanical, chemical, and electrochemical. The ones we talk a lot right now is the battery, which belongs to electrochemical energy storage systems, mainly because they have high energy density, amount of energy we can store per unit mass or per unit volume. And also they are fast response. As soon as you plug it, you can use them. High efficiency is the energy loss between charge and discharge. So you can notice all this energy storage system is doing some sort of energy conversion from different source, eventually convert into electrical energy. That's the most convenient form human can use. Every conversion will lose something. It's just a natural law. So in this case, electrochemical energy is the most relatively higher efficiency. And it's relatively scalable too. So ideally, this is an example. We pair up with batteries. In this case, it's a demonstration of lithium-ion battery. Pair up directly with the wind film. Or you can do this with the solar farm too. So what is this about electrical vehicle? How does it fit in? So if you look at the total CO2 emission by sector, which kind of business is using the fossil fuel? A quarter of this is coming from transportation. And if you break down the transportation, 75% among these are the cars running on the road. So basically, if we can try to find a way to just tackle this, replace all the fossil fuels that we're using on the car, we already kind of solve a huge chunk of the problem compared with all the other things we need to do on the side. That's why there's a huge move trying to deal with the electric vehicle. Okay, so lots of countries has been working on investing batteries, electric vehicles. France as well. Starting from 2018, there's a huge investment which result in 6 giga factory, which will directly create 10,000 jobs. If you look at the map, 5 out of 6 of these gigafactory that's being invested, they are all near us. They are all in Hauts-de-France region. That's why now they are calling the Hauts-de-France region the Battery Valley. So it's really highly relevant to us right now. What does that 10,000 job means? If you look at the total job vacancy in the last trimester, you can see this represents the 2% of the nationwide job vacancy. Of course, this is not the best calculation, but it's just to put you in context how much does this represent. And we know 5 out of 6 is in this region. If we take this into account for the Hauts-de-France, this represents 22% of the job market. Okay, so what is the current challenge for batteries? Usually we analyze the batteries or energy storage systems by their energy density, how much energy they can store per unit and per volume, and their power density, how fast we can draw and charge these batteries. So for the electric vehicle sense, this represents one charge, how far I can drive. This represents how much time it takes for me to dock and then get a full charge. So you can imagine we want high power, we want high energy. This is what we are going for. So a lot of the R&D activities, no matter it's in industry or in academia research, are going towards this. And a lot of the solution provided, especially using lithium metal, is going for high energy. So this is how a battery usually look like. We have 2 electrodes and a separator. The conventional ones are usually immersed in a liquid electrolyte. So the most common negative electrode is graphite, and positive electrode is metal oxide. So to store more energy, the trend is to replace the graphite into lithium metal. This will increase the energy density by 10 times, theoretically. Of course, there's a lot of challenges because you change the chemistry, you change how the cell is working completely. And this also is one of the main sources you see those boom and catching on fire because lithium metal form is highly reactive. So the other challenge is where we are chasing for faster and storing more energy, how can we do this in a safer way? So why does the lithium-ion battery catch on fire is because if we are plating lithium metal, they are never going to be uniformly plating. Often they have local hotspot. They will keep growing from there like a needle shape. We call it dendrite. Eventually, it goes through the entire battery and puncture through the separator. That gives you a short circuit inside the battery. So you directly connect positive and negative electrode, you have a huge energy release. That's how we catch on fire, basically. So there's a huge trend on solid-state batteries. The concept is to, if we put a physical barrier in between, replacing this as a hard barrier, maybe we can stop the dendrite to grow and puncture through. That's why you hear a lot about the solid-state battery, because we want to chase for high energy, also make sure it's safe. Another major challenge is about the cost. So electric vehicle is still more expensive, and if you look at their cost, it's majority coming from the battery. The battery inside the electric vehicle is the most expensive part. If you break down the cost of the battery, you can notice the most expensive part is the positive electrode. If you look at what they are usually made of, it's this lithium, nickel, manganese, cobalt oxide. So just to give you a sense, this is the price of 2018 and 2020. In 2 years, you can see how much this important element for making the cathode material increase. So this is, of course, because of the demand, but also because the mineral resources is not very homogeneously distributed in the world. Just taking lithium and cobalt as an example, the upper part is the lithium, here is cobalt. 90% of the lithium is held by these 6 countries. 90% of the cobalt is held by these 6 countries. That's just for the positive electrode. If we look at the negative electrode, the graphite, it's the same thing. It's not very uniform. And one thing you might notice, nothing is in Europe. So this is also a national security. That's why it's important to push through for certain countries to have their strategic plan moving towards this net carbon plot. Okay, so what's the solution? We cannot really change how this works, right? So we need to find other solution. So a huge part of the effort right now is trying to replace lithium ion to sodium ion, because sodium is from the seawater. You have much more abundancy on Earth. The other thought is also to find other cathode material to replace the cobalt and the nickel, to see if we can choose something else that is more abundant, like iron or phosphorus, sulfur. That's also a possibility. So that's the general concept of where the research is going. So to the research, myself specifically, I am focusing on looking at the electrolyte interface. So if you look at the composition, as I mentioned, I show you a little bit earlier how the structure of the battery. So during the charge and discharge of the battery, we have the electron that is going from outside when we connect to our device. Inside, we will have cations, often is lithium ion, that is swimming across the 2 electrodes during the charging and discharging. So a lot of important challenges, degradation, kinetics, how fast you can charge, lies at this electrolyte-electrode interface. How does the electrolyte molecule arrange on the electrode surface? How exactly does the lithium ion go through this interface and sit inside the electrode? These are the important questions no matter which system we study. We need to fully understand the charge storage mechanism to help to give answers why this does not work or why this one works better. So we have a better material strategy and processing strategy as well to build better batteries. So I'm just going to give you quickly 2 examples later. So what I do is I use something called atomic force microscopy. For those one who doesn't know, it's basically like your finger. You use your finger to trace the surface, you know the topography, and you can also push the surface, you know how hard, how soft it is. Just this fingertip is nano-sized. So you can see this is atomic force microscopy probe. You can see it's very small, the probe, about a few millimeter. If you zoom in on the end and flip it upside down, you can see there's a cantilever about 300 or 400 micrometer. And the tiny tip at the end is ranging from 10 to 50 nanometer. That's our fingertip spatial resolution. So you can imagine we can get down to molecular scale, understand a lot of things at very high spatial resolution. So when it's under operation, we have a laser shining on the backside of the cantilever, go to the photodetector. This will help us to record if the cantilever has attraction force or repulsive force. This will tell us a lot of things. And also with the spring constant, we know how much force the cantilever is feeling by this way. So this is how it looks like in reality. This is our AFM, one of the old AFM I work with. We have a sample stage that controls the sample XY movement. We have the AFM head. If you look from the side, it looks like this. We mount our AFM tip at the tip holder here, which will control the Z direction and also tell us the force. We can then put our sample underneath, or our electrochemical cell, our batteries underneath. This is how it looks like, just to show you quickly in reality how it looks like. So some quick example just to show you what kind of thing we can do with AFM in the electrochemical system. So I mentioned it's important to visualize or to understand how the molecule is oriented. So with AFM, you can then easily image this. So this is this electrolyte is a pyrrolidinium 1,4-TFSI. They are kind of a bulky kind of molecules. If they sit on the graphite electrode, you can see in the AFM, we can image in liquid. This is the first adsorbed layer of the molecule on top of the surface. You can see we can clearly go down to very high spatial resolution. This is 5 nanometer. So this helps us to understand what exactly is going on when we put electrolyte on the electrode. Of course, this is a battery material, so we want to polarize the surface. You can see those older structure is changing when we polarize the electrode. This all help us understand better in the battery cycling, what is happening when we polarize the electrode. Okay, the other thing is about volume change. This is also an important topic. When we put lithium ion inside the electrode, it's like blowing air into a balloon. It will expand, it will contract. And materials always have a fatigue. There's a limit they can do this expansion and contraction. So it's important for us to know to which extent this is doing, how much expansion they experience. So using AFM can also tell us this. The concept is just putting our AFM tip directly in contact with the surface, and we cycle our battery and track the volume change locally. So just to give you a quick example, these are the two materials, that's tungsten oxide family. They just have different structure. You can look at this figure. In this case, we are cycling H2SO4. We put proton in. You can clearly see when we try to proton in, there's an expansion. We take proton out, there's a contraction. Same thing for this material, but you notice this one has a much larger hysteresis. This one doesn't really care much. It's very reversible. And this also shows up in their electrochemical performance. This one has a very poor power performance. When we try to cycle it faster, push it to charge faster, it lost a lot of its capacity. This one doesn't care much. This all link back to its microstructure because this one already have their channel open. So the proton can go in and out very easily without forcing through the structure. Of course, with the microscopy, we do heterogeneity study. We want to see localized area. Is there any differences with the expansion and contraction? So this is just very quickly to show you the material has this grainy feature, and you can see the volume expansion. Some of the grain is very small in expansion. Some of the grain has a much larger expansion. Of course, there's more in-depth study to pair up with their microstructure and why does it do this, and how will that impact the performance. So I was originally from Taiwan, and I did my master in Europe, Erasmus Mundus, focused on materials for energy storage and conversion. The main headquarters is actually in Amiens, in LRCS lab. And then I follow up with a PhD in Toulouse, working on supercapacitor, and then move on to the US Oak Ridge National Lab for a postdoc, turned into a staff scientist there for 3 years before relocation back to France, Lille. With that, thank you. I can take a question.